fatigue life criterion. So now we are going to get into real serious design with this, with what we have so far, Goodman-Langer lines. Okay, so this is the plot which is experimentally obtained, as I mentioned before. The circles indicate each stress level, the sigma A, sigma M, at which some material failed, and this is normalized against the endurance limit and ultimate strength. So you can plot a lot, you can plot pretty much every material you can think of on this plot by non-dimensionalizing. Okay, so we've seen that, for example, that in compression region, this line is more or less flat because it explains a lot of plot points there, as you can see here, these plot points. And then in the right-hand side where you have tension, this Goodman line sort of gives you it gives you like it doesn't really pass through all these points. Ideally, you want to pass through this point so you can predict failure for them, but it sort of gives a conservative estimate of that yellow envelope. So it's sort of conservative in that sense. There is a problem with Goodman line. It doesn't really explain this. Not explained. And then it's too conservative here. Okay. When you say it's conservative, what it does is it means that when you design it based on this criterion, Goodman, you will end up with shafts which are much larger in diameter, and that's going to unnecessarily cause you more money in terms of manufacturing. But even when you want to run this with a heavier or a bigger diameter shaft, it's going to cost you more money. Like the operating cost is also higher. So this Goodman equation is simple. It's non-conservative for compression. It's saying non-conservative because you can see it's very close. These points are so close to that. But on the tension region, it's not conservative because those, the yellow region is kind of spread out. It's conservative for tension, as I said, non-conservative for compression. It's simple, that's nice. And then what we're going to talk about in this section is other curves, which help you to model this. So all these things we're going to talk about next are all equations obtained from empirical equations. Just looking at this plot, you fit lines, and that's what it does. This is the Langer line we've learned. We've seen the Goodman line, which let me draw with blue. And there are a host of other lines which we'll be talking about today. This will be the Gerber line, ASME-Elliptical, Soderberg line, and we won't get into the other two. Probably, yeah. So Goodman line, we've seen that before. It's simple, conservative. So by the way, I posted this on Blackboard. I don't want to write this down. It's just not worth it. It's just essentially a model for those equations, right? And then you just need to know how to use it. So failure criterion is that equation of this line, which passes through SE and SUT. That's why you see SE in the denominator, SUT in the denominator like this. And then if you want to find design equation, you substitute sigma A with n times sigma A, and then you get that equation. So that gives the design factor. So this predicts failure. This line gives you a factor of safety. Okay, so next, look at the next one. The Gerber line. Okay, it basically is joining 2 points, SE and SUT. But we've seen this joining this line through the Goodman line, but instead of joining a straight line between the two, it basically creates a parabola. Okay, the equation of a parabola, if you don't remember, it's either y square equals 4ax or x square equals 4ay. Right, and so you see this, that this is sigma m is x square plus something about x square, something y divided by some constant, so a0, a1 equals 1. It's the same equation, you just have to put it in this form. Okay, so then this is based on the observation that if you go back here, wouldn't be better off if he drew a parabola? And that gives you a better line. That's why we have that line. Okay. So then how do you use it for design? You substitute sigma A with NF sigma A, sigma M with NF sigma M. You put it in this equation, this first equation, and solve for NF. Turns out that you will not have a straightforward expression. You have a quadratic expression, which means that you need to use that discriminant and minus b plus or minus b square minus 4ac. If you remember, and it gives you this formula. You don't have to remember it. I'll give it to you. But that's how you use this line for design. Okay, the next one is the Soderberg line. Here, what we do is we join SE with SY. Okay, and this is very conservative. Let's look at how it look here. So this is SUT. SE is somewhere. SE is, so it joins. Hold on. SY is not shown here, so I don't know. SY, if SY was here, it'll just join SE to SY. Okay, so you can see if you go anywhere down, you're going to be super conservative. So if you want a very conservative design, then you want to go for Soderberg line. So I think it makes sense to have such a line for some things which you are anticipating there will be a worst case load of a very high magnitude, but more or less, you'll have a normal loading, which is not that high. And so that equation is again a nice straight line equation. It passes through SC and SY. And so you'll see that SC and SY is the denominator. That's the point at which it intersects the X and Y axis. And then for design equation, you substitute sigma A with NA sigma A and sigma M with NF sigma M, and then you get that equation. Okay, the last line is the ASME-Elliptic equation. I think this is the most popular one. It's the one where you join SE with SY using a parabola. Well, not, sorry, my bad, not parabola. It's a, what this is? It's an ellipse. It's an equation of an ellipse. X squared by A0 plus Y squared divided by ellipse. So again, you can look at the plot and see if this makes more sense when you look at those dots. And for some cases, it does. So that equation, and then NF can be found by substituting sigma and sigma M by N times sigma. Okay, so what we'll do is we'll try to put all this, what we have seen here, into a problem. And that will be the end of this chapter. It turns out this question is not so different from the previous one, right? The previous, we have done this. In fact, we've done this problem for the Goodman band. We already computed NF for that. Did I change the values 100? No, it's the same. So it's just a matter of using these equations for the other two, other three, B, C, and D. So let's just do that. So first of all, just like before, this is, yeah. Yeah. So this is not going to affect the NY. It's only about NF, just new ways of estimating NF, which is this, which is the infinite life, right? So we're just finding new ways of estimating. We're just trying to find better ways to use the fatigue line, either this one or that one, this one, or I think the third one I missed from this figure was the ASME-Elliptic, which goes this way. Okay, so the same settings, sigma, sigma. So we have sigma max is 60, sigma min is minus 20, and then we have the usual SUT is 100, SY is 85, SE is 40. So sigma M is the average stress. -60 minus 20 is 20, an average. Sigma A is half of the difference. 60 minus 20. 40. Okay, now we can start working in the equation. Oh yeah, okay. Sigma M prime is KF sigma M, so 1.2 times 20, 24. Sigma A prime is KF sigma A, 40, which is 48. If that's just a formula from the previous pages, sigma A, in this case, is sigma A prime and sigma M prime because of the notch. 48 divided by 40 plus 24 divided by 100 was that is 0.69. Okay, not a very good factor of safety. It's less than 1. So this is probably doesn't have an infinite life. It probably failed during finite loading, the finite life.
For this question, we don't need to tell that.
Right, just applying the formula, right? You probably never get a problem like this. It's too simple. You'll probably get a problem which is more applied, where you are doing some inference more than just subbing in the values. No, only this is only for infinite. These lines are only for NF. The NY is the same. Okay. I mean, that's the question we did in the previous section. Is a very valid question where you are told to compute if the whatever that material net loading condition will fail infinite, and then I can just combine it with the previous sections and say if it's going to fail in finite life, then what is the life expectancy? For that, you'd have to go back to the SN equations and get that. Right. Okay, so let's do the second one, which is Gerber. It is a long formula, which is the one which involves a quadratic equation. So B Gerber. That equation is NF equals half UT square sigma A divided by S E. Now, pardon the square root sign, 1 plus 2 sigma M S E sigma A S U T square. Okay, I'm just going to do well, sigma mu. I want to put the primes there. Okay, so let me not, you know, the values for these parameters. I'm just going to give you the final answer. It's 0.8.
This is still finite,
Everything is, yeah, this is going to be finite, right? But you don't know what ny is. So unless you know ny, you cannot predict that. If ny is less than 1, then it will not be finite line. It'll fail. So you're not sure. Soderberg. Soderberg and ASME-Elliptical. Sigma A prime divided by SE plus sigma M prime divided by SY. That works out to be 0.67. Then we have ASME elliptic. That formula is NF equals square plus
but this question is not asking for NY. But like you would have asked a problem with the
Same.
all the set.
right. There's only one ny which comes up. They're not different nfs. Okay, so let's just sort of time, but let me just summarize what we have seen so far. So I'm just going to list all the nfs for the different criterions.